Good evening. I'm back for what I suspect will be the second to last recording to complete this BC ESQ model for quarter two that was created a couple days ago here in 2023, October 2023. But there's a chance I'll just keep going. It's a little intimidating. It looks like at the bottom I've got like 27 pages left or 27 problems left. Somehow I feel like it's smaller than that and it's closer to like 15 to 20. Maybe there's just some extras in there, but I'll go as long as I can. Yeah, I'll go as long as I can. So this is part 3 of this video. I believe I worked through questions 1 through 5. Yesterday I worked through 6 through 8. And today I'm going to work through at the very least 9 through 11. I might possibly go all the way through to the end of 14. So rather than keep talking about it, you get the idea. If you're in Calculus BC at Franklin, odds are you've gone through your fair share of ESQs. So here's me doing another model. And I'm moving really quickly through these. I think you've probably realized that. I'm working through them really quickly. I didn't get LCALP approval to get compensated for this. I just wanted to do it because it looked like it needed to be done. So I'm going to move through it a little bit quicker and not do the slow, methodical, careful, let's make sure every base is covered method. It's an ESQ model for a course where every single person in here has passed Calculus AB already. I trust that your AB skills are fairly strong. Now, to kick things off, we're going to look at question number 9. Question 9 focuses on setting up integrals that represent the volumes of solids of revolution. And in this case, even though you haven't seen the cylinder method yet, I am going to show you the cylinder method with each of these. So in fact, I probably should have, when I created this, added a second one here just to kind of illustrate what's happening. I guess I can copy it once I draw the region. Yeah. But in any event, I'm going to do this both ways. So this is a problem where traditionally when I give this ESQ, you have the opportunity to earn a bonus point by setting up the integral for this volume that we're trying to compute here in a second different manner. And that's something that you can do once you learn what's known as the cylinder method. So I'll demonstrate both of them. I will always start with the method that you know best, though, so just keep that in mind. So to kick things off, for question 9a, we're supposed to set up an integral for the volume of the solid formed by revolving the region, it looks like it's missing the words the region, bounded by y equals the square root of x and y equals 0 on 0 to 4 about the x-axis. So first of all, we can set that up really quickly. We have the square root of x. We have y equals 0, which by the way is just the x-axis. And we have that it's going from 0 to 4. So that's nice. It goes right there. We get a nice little half dome thing. This is 4. In fact, I can put this up here. This is 4 comma square root of 4, which is 4 comma 2. And then as it says, we're revolving it about the x-axis. So we're going to revolve it this way, which is going to create a nice little reflection down here. There is our region from the side, our solid really. From the side, we're looking at it almost like a two-dimensional cross-section. To help us see the circle on the inside, I'll draw a little representation of the cross-section. So there we go. Now, for us to do this using what we know as the disc and washer method, the only method that you know prior to learning the cylinder method, just as kind of a note. Oops. If you're trying to figure out how to set this up, effectively what we're going to do is we're going to imagine that, I'm not going to imagine, we're just going to do it, what the heck. We're going to figure out what the radius would be for each of these cross sections. Like we need to find a representative expression for the area at any x value in that region. And then we can use that, and you can use integration to add up all of those little areas. So in this case, we've got one single radius. This is a disk problem because the cross-section is a solid circle. The radius of that is going to be top minus bottom. I'm just going to abbreviate that bottom. No, I'll write bottom. It's fine. It's fun to say bottom. And then from here, top, looking at our sketch, the top is square root of x, and the bottom was 0, which means our radius is square root of x. Now, if you're wondering like what the point of that is, well, the idea is what we're adding up here are a whole bunch of pancakes, basically. That's what I had for dinner, so they're on my mind. We're adding up a bunch of thin little pancakes that are slowly being added across. Each one's dimensions get bigger depending on sort of the bounding that the curve itself offers. And what we're going to do is we're going to sum up the areas of all those infinite thin little pancakes. So each of those pancakes has an area of s squared. And so our volume that we're looking to calculate here is going to be equal to the sum of all infinity pancakes, each of, how did I write s squared? Okay, you can tell that I'm not feeling my best. So this should be pi r squared because they're circles, not squares. Squared something, I wrote the r for square, my bad. We're going to be adding up all those little pi r squareds. and then multiplying each one times a tiny little thickness. In this case, it does become a thickness dx. We're going to go from x equals 0 to x equals 4. I'll actually write the x's in this case, just because that's going to change in a second. So now from here, what you'll typically see is the pi gets pulled out in front. That's a favorite of mine. We'll then multiply pi times the integral from 0 to 4 of whatever our radius is squared. And in this case, our radius is going to be that square root of x. So if we clean this up a little bit, we get that this is equal to pi times the integral from 0 to 4 of x dx. But in truth, I wouldn't even bother going that far. The answer I'm looking for is right here. We're just supposed to set up an integral. There's a perfectly set up integral that maintains that structure, so I can really quickly see that you've done pi r squared. And again, just our radius depends on the height of the curve, so we plugged in root x for that radius. So this is our typical method. This was using disks in this case. And notice that our disks were perpendicular to the x-axis, so we were in terms of x. Now down below, what I'm going to show you is something that, again, as of October 11, 2023, we have not covered in Calculus BC, but by the time you watch this video, I don't know, I don't want to predict your life. Maybe you're going to look at this, I don't know, later on in the quarter when you realize you're struggling with question number 9. Here's a good opportunity for you to nail it down. So to attack this in a second method, known as the cylinder method, what we're going to do is we're going to add up an infinite number of really thin little cylindrical shells. Now it's a little bit awkward. I don't want to go into the full derivation here because that's not the point. You would only do this if you knew this technique. But effectively what we do is you imagine a bunch of paper towel rolls, except there's like a whole bunch of them. Their height depends on how tall the curve's the region is. So in a sense, we can imagine one such paper towel roll right there. It'll be totally hollow on the inside, by the way. I'm choosing to call it a paper towel roll for a reason. And then basically we have a whole bunch of them around it. So for instance, just for this one time, I'll pretend like you don't know it, or I'll acknowledge that you might not know it. There's one in there. We can get a really, really narrow one in here. And effectively what we do is we end up filling this whole thing in with a whole bunch of stuff. If you're a hockey fan, it looks a little like the Stanley Cup, except green. Maybe if someone had an alfalfa farm or something, they would look that way. But in a sense, that's what we're going to create. We're going to add up a bunch of little cylinders. Now for these cylinders, we're adding up not the volume or the area or anything. We are not the volume, but we are adding up the lateral surface area. And the formula for that lateral surface area, sometimes you'll see it as S equals, I'm going to call it A, so A for that area, is going to be 2 pi RH. That's going to give us that outside area. Imagine taking that outside paper towel roll and slicing a line down one side, and then unfurling it, you're going to have a rectangle. The length will be the circumference of the circle, and the height will be h. So in a sense, looking at this picture, this is h, and then this is going to be r, as we've done before. And so now we need to find our way to represent it. Well, as I said, you'll only do this if you know how to do this already. This isn't me teaching this lesson. I'm not going to do that in ESQ model. It's definitely not worth it for me. The lesson's coming. But at the same time, we can set up all these pieces. In particular, we can note that the radius in this case is going to be right minus left. And as soon as you hear that the radius is going to be right minus left, I think you can kind of figure out all of those pieces. Oops, excuse me, that's not true. The radius is perpendicular. There you go. So basically, like our radius is perpendicular. Our radius is just going to be the height that we are at on the curve, and that's at a height of y. So our radius is going to be top minus bottom, y minus 0. And our height is going to be right minus left. That's what I should have said before. I apologize. Our height will be right minus left. And our height is going to be the right, which is 4, minus the left, which is this curve. But because we're going right minus left, we need to be in y terms here. So that is sort of the cost of being able to set up the second one, is we have to kind of switch things around. And if our original function was y equals x squared, then pretty clearly you can square both sides and get that x is equal to y squared. So our height will be 4 minus y squared, because it'll always be on the right at that line, that vertical line, x equals 4, and then on the left it'll always be the curve. Given this, to set up our integral, we're going to do the integral of 2 pi RH times that little dx. And in this case, we're going to go between y values. So we're going to start at the x-axis, y equals 0. And we'll go up to the top intersection point, which is at y equals 2. And from there, what I typically will do, what you'll see is I'll pull out the 2 pi in front. Our integral will run from 0 to 2. Also, apologies. That should have been a y. Shouldn't have even bothered with this. I shouldn't have been trying to teach it. I should have just absolutely just done the problem. This is my mistake. I don't have time to go back and do it again, though. I apologize. So our radius will be y. Our height will be 4 minus y squared. And then, of course, we're in terms of y. So there is our volume integral. And again, this is in terms of y, the other's in terms of x. That is always true. It will always be true that one will be in terms of x and one will be in terms of y. And otherwise, we've used one method. We use discs. I mean, that'll be true. One of the methods will be discs or washers. The other method will be cylinders or shells. This is the cylinder method. In that case, it runs parallel to the axis of revolution. So like I said, I apologize for attempting to do any sort of instructional information here. I shouldn't have done that. Like, this isn't the time for that. And I stumbled over it because I didn't rehearse that. But yeah, there's your two versions of the answer. The second problem we're going to look at from section 9 involves a region that's bounded by 2 powers of x, which works out really nicely. The intersection points come for free. They end up being the origin and the point 1, 1. But this time we are revolving it about the y-axis, so we're going to be revolving it right up here. As far as our region, we're bounded between x to the third and x to the sixth. It can be a little weird to draw this. I usually think about this as being an banana kind of drawing. So we get some sort of thing like that. That actually turned out really banana-esque. Go like that. I'm trying to make it a little bit curvy to be as accurate as possible. There we go. So there's our banana. We're revolving it about the y-axis, so the reflection is going to be over here. Again, that looks like they aren't quite perfect, but there it is. We've got everything revolved nicely. And then I'll go ahead and copy this down so that we can be ready to do that with cylinders in a second. Now for our first one, though, we're going to stick with the AB techniques. So we're going to set this up using washers. Our washers are going to be perpendicular to the y-axis, though, so very important to know that. Notice that. So we are perpendicular to the y-axis. That means we're going to be in y terms, or specifically it means we're going to be washers in y terms. So that's exactly how we're going to set it up. When we go to do our 2 radii, we'll call them big R and little r. They're going to be using right minus left to calculate, or to calculate their lengths relative to the coordinates on the grid. And basically we're going to need to solve for y, so I'll go ahead and do that right here. We'll get x equals the cube root of y, and x equals the 6th root of y. I know there's a plus or minus there, but keep in mind our region was in quadrant 1, so we don't need to worry about the plus or minus part. Just the positive will do. Thank you very much. As far as which one's which here, I didn't make a big deal out of it. But the bigger power of x is always on the bottom. So this will be x to the 5th, and the top one will be the the top one. Why did I put x to the 5th? I meant x to the 6th. Sorry. This will be x to the 6th. This top one will be x to the 3rd. And that's helpful because when we go to do right minus left for the radii, when we do right minus left, then we're going to be using the y-axis, which is x equals 0, and whichever the curve is in its radical form. So for instance, on the first one, the right curve will be the 6th root of y. So I'm going to put in there that big is 6th root of y and little is 0. And then the other one will follow suit pretty cleanly, the cube root of y minus 0. Now having done all that, we can set up our volume integral. It's adding up a whole bunch of little slices of pi r squared of circles, really thin circles, but circles all the same. But I'm going to factor out that GCF of pi, or just pull out that scalar of pi. Our region is between x equals 0 and x equals 1. That's true for all of these. If x to the 3rd equals x to the 6th, that means that x is equal to 0 and 1. So there are limits of integration. As far as what goes on the inside, we're going to have, it looks like the 6th root of y squared minus the cube root of y squared. And then all of this will be in terms of y. So there is our integral. Again, this is definitely a problem that you could handle back in calculus AB at the very end. It's the last unit we covered in there, at least at Franklin. Now when we go to look at the other one though, again, if we did washers in y, the other option we're going to use then is cylinders in x. Those are the complements. If we did cylinders in y, then we do washers in x. They complement each other. So to draw our cylinder, I'm going to pick out a spot here. I'm going to sketch a representative little shell here. Remember, this is like part of a paper towel tube. It's a really small part of it, but a part of the paper towel tube altogether. So it's not full, it's not solid. You'd be stacking a whole bunch of these on the inside. But that one's nice and representative. That's worth reminding you that the area of that lateral area specifically of a cylinder is 2 pi RH. And that tells us what we need to find in this case. We need to calculate what R is going to be, and we need to calculate what H is going to be. Now, H is really easy to see in this case. H is just going to be our top minus bottom. That's going to be, in this case, x to the third minus x to the sixth. And remember, since we're setting these things up, if you're ever not sure if you've ordered things correctly, remember to put absolute values around your integrand. That will absolutely get you credit for the setup at the very least. And on the ESQ here with this question, it's just setup, so that's a good idea. As far as the radius only depends on the shift and the variable that we're using. We're trying to describe this distance, and that distance is effectively whatever x value we're at. So our radius is just going to be right minus left, x minus 0. So sort of interesting, definitely something to get used to, especially those first couple times. It takes a little bit to get your mind around, but you have tons of resources to do that. Last, I'll set up my integral for the volume. I'm going to take 2 pi out in front. We'll do 2 pi times the integral from 0 to 1. These will be x values, by the way. They were y up above, but they just happen to be the same. And then inside here, we're going to have our radius, which is x, times our height, which is x cubed minus x to the sixth. And if your question is, wait, how did that's so easy. That's so clean and simple to calculate with. Yeah, it is. It's really nice. Like using cylinders for solids formed by revolving about vertical lines. Total game changer, folks. Total game changer. And yeah, there is 9b. And FYI, if you're wondering about something looking different or seeming different or me seeming different here, it's because I did these out of order. I've been swearing at the computer a little bit. Sorry. Not sorry. I keep making mistakes. The third problem we're going to attack is going to be question 9c. That's a region bounded by 3 lines. The diagonal line y equals 2x, the horizontal line y equals 8, and the vertical line x equals 0, which you probably know is the y-axis. This time we're going to revolve it about the line x equals 6, which definitely adds some complicating factors to it. In fact, it might be smart for me to move this y-axis over a little bit, just so I'll have a little bit more room. Since x equals 6, this little line right here is somewhere in this ballpark. So we definitely got some work to do here. So in order for us to set this up, I think you can probably picture what's happening here. We've got this line y equals 2x, this line y equals 8. Excuse me, let me make that a little bit stronger. And then the y-axis itself, it creates this little like slice of pizza diagonal region up here. And then of course that's going to end up getting reflected to the other side. Notice I'm not finding any of the actual intersection points just yet. I'm going to do that in a moment. I just wanted to get a visual representation of what this looks like here. So effectively there is the cross-section and its reflection. Let's give myself a little bit more room here. And then from here I will draw our little cross-section. Our cross-sections are going to be washers in this case. So we'll be able to draw some washer-based cross-sections here in just a second. But notice that these cross-sections are perpendicular to the y-axis, so we're going to need to be in y terms in order to do this with washers. So this will be the washers in y in order for us to go forward. Now how did we set up washers in y? Well, first of all, the area that we're using in this case, the area expression that we've got here, is going to be the difference between two circles. It would be the area of the big circle minus the area of the little circle. Both those radii are, of course, changing in this case, or potentially could be changing. I don't think they both are in this particular case. And then that's going to boil down to us figuring out what is the big radius and what is the little radius. We'll continue using right minus left in this particular case, but it's important to note that our actual region is over here on the left. So when we do right minus left, we need to make sure we're using the correct right and left. It'll be these pieces with the axis of revolution at x equals 6 being on the right. So setting that up, if we want to talk about the big radius, that's going to be right minus left, and our left is just going to be the y-axis, which we know is 0. So the big radius will always be 6. That makes sense. That's a vertical line on the outside, so this solid will look like a cylinder from the outside. As far as the little radius, we'll again start at the axis of revolution at 6, and then on our left, we're going to have y equals 2x, but because we're in y terms, we need to figure out how to write y equals 2x in the appropriate form, which will be x as a function of y. Fortunately for us, that's not hard. I'm going to multiply both sides by 1/2, and I'll get that 1/2 y equals x, which is exactly what we're going to call this, 1/2 y. Now, given all that, remember we're only setting up the integral. We don't actually have to do the work. So as our volume, we're going to have, I'm going to GCF out that pi from both of these expressions. Some like to leave it inside. I prefer to pull it out myself. We'll deal with the limits of integration in a moment. For the inside, we're going to have big R squared. So in other words, we'll have big R squared minus little r squared. And then all of this will be in terms of y. As far as those big and little r's, we're going to have 6 for the big R and 6 minus 1/2 y for the little r. As far as our limits of integration, we're doing this in terms of y. So we've got to think about what the smallest y is on our region and what the tallest y is. But you can actually see that. This was y equals 8, so the biggest we're going to get to is 8. And the lowest was at the, the x-axis, y-axis, the origin, which will be 0. So our integral will run from 0 to 8. So there is, Clemson colors for some reason. There is our washer volume integral. Again, don't have to evaluate it, we're just setting these things up. Now, having said that, having done this with washers once, that's great, but this isn't actually the most expedient way to do the problem once you've learned the cylinder method. So I definitely want to illustrate the cylinder method for you as well. So down here, this is still once again labeled nicely. We are still revolving it about that vertical line x equals 6 here. But when I go to draw my cross-section, or my cross-sections, they're going to be different here. Because in order to keep our setup in this way, we are going to draw our little mini cylinders. And again, cylinders should be straight up and down. So it's like a cat superhero for a second. So there is our stuff. It looks a little bit like a hockey puck. I usually mention like paper towel rolls. Imagine you've got your paper towel roll and you've got a bunch of different sized ones depending on where you're at. They're all hollow on the inside and infinitesimally thin. But as you probably remember, the volume of the lateral area of a cylinder is 2 pi r h. And there's a cool derivation you can do. I would encourage you to just cut open a paper towel roll or a toilet paper roll and just look at it when you lay it flat. I think you'll see that it's circumference by the height of the thing. Kind of cool. Now for us, the cool thing in this case is that we are going to be in x terms when we do this. That's just one of the unique things about cylinders. Also, if washers were in y, cylinders have to be in x. And of course, we're going to use shells or cylinders. And I prefer to call them cylinders myself. I can see it a little bit better than shells. I picture like shells that had abalones in them. So when I hear shells, your call. So in this case, when we go to set this up, we have 2 dimensions we have to account for, the radius and the height. The radius itself is always dependent on 2 things. Specifically, it's dependent on the axis of revolution and the variable that we're using. So in this case, we can look at this point as being x units out. And we can calculate our radius by using right minus left and saying that this will be 6 minus x. That will give us our radius length at any point. I might encourage you, if you don't feel like that's intuitive, to draw a few more cylinders at different heights and kind of see if that makes sense why. It is a little bit tricky for sure. It might be something you have to just remember at first. I struggled with this in high school. It was probably the first academic thing in high school I really, truly struggled with. After that, our height is going to be top minus bottom. Our top in this case is the horizontal line y equals 8. And our bottom is going to be that line 2x. With both of those pieces in place, we can set up our integral, like really lickety-split here. I don't know if that's actually a fun thing to say or not. I have no idea. In any event, our volume will be the integral of all those little 2 pi rh's, but I'm going to factor out or pull out that scalar of 2 pi. It's then going to have our radius of 6 minus x times our height of 8 minus 2x. If all those minus signs make you uncomfortable, remember you can slap an absolute value on the integrand and you're covered completely. This will all be in terms of x. And then last but not least, we do need those intersection points. And we didn't have to find it on the previous one, but it is necessary for us to figure out where those 2 things cross. And well, if we have y equals 8 and y equals 2x, those things pretty obviously intersect at x equals 4. And in fact, that's what this point is right here. This is at the point 4, 8. So as far as x values go, our limits of integration are running from the far left one, which is here at 0, over to the far right one, which is at 4. So our integral will run from 0 to 4. Now, if you don't trust that this worked out properly, I'd encourage you to use your graphing calculator to plug in both of these and verify that they do in fact come out the same. If you don't get the same answer, check to make sure that you put pi and 2 pi. It's a really easy mistake to make when you do this. You do need both of them there for this to be accurate. But yeah, there it is. There is our third one. And then finally our fourth one, in a sense, it's just kind of completing the set. So we did all of the ones earlier. We did about the x-axis and y-axis. We just did about a vertical line that was positive. Now we'll do a horizontal line that's negative, just to kind of complete the set. So first of all, that's going to be y equals -1. I'm going to go ahead. Oh, it won't let me. Okay, whatever, stupid thing. I have no mood for this, so let's just skip that part. So for our first option, let me sketch the curves. We have a radical, which will be concave down, and we have an exponential, or excuse me, a polynomial, which is going to, in this case, be concave up. So based on that, there's our little petal. I want to exaggerate it a little bit more just so it's a little easier to see things. There we go. I'll draw my little leaf a little bit better. There it is. And now that covers our region and its reflection. Just oh, no, it doesn't, because we're revolving it about y equals -1. Oh joy, I'm making mistakes again. So there is our axis of revolution. Again, we're revolving it about right there. Means there's going to be that little sizable gap here. So there we go. And now that we have this ready, we can sketch out our two integrals. Oops, let's give ourselves just a little more room. I was going to say give ourselves a round of applause, but I don't deserve that. I have to go re-record questions 9A and 9B. My body falls apart. So, okay. So we got two options here. The first option I'm going to go with is our classic one. From Calculus AB, we would definitely use the washer method because that was the only method that we developed. So just kind of sliding it in here. Let's get it in. There's our stuff. We're going to need to account for the big radius and the little radius of this guy. The big radius is going to, of course, just like the little radius, be top minus bottom. But here we want to go the biggest radius possible. So the top in this case is the 4th root of x. And the bottom is going to be the axis of revolution, which is y equals -1. So it'll be the 4th root of x minus the -1, which you'll know as the 4th root of x plus 1. Likewise, if we go to do little radius, that's going to be the little radius that runs from here to here. So right in there, I know it's really hard to see. I'm just trying to kind of, there it is. There it is. In this case, it's going to be x to the 5th minus a -1. I almost changed it automatically. So those are our two radii. Now that we have them, the rest of the problem is trivial. It's the same setup every single time. Our volume will be with the pi factored out in front. It will be the integral of, and then we're going to have the 4th root of x plus 1. I'll just go ahead and simplify that. Minus x to the 5th plus 1, all squared. All in terms of x. And then for our limits of integration are going to run from 0 to 1 because our interval, or these two curves intersect on 0 to 1. Now, having said that, that was the first way. We did this with the washer method. In fact, let me label that as such. This was us using washers. We don't have to use washers once we've established and learned the cylindrical or shell method. So that's going to be my other option. I'm going to go down here, and I'm going to sketch out a nice cylindrical shell. Recall that cylindrical shells have area, lateral area, 2 pi rh. And that means we need to figure out an expression for the radius, and we need to figure out an expression for the height. So height is going to be right minus left, and the little radius is going to be top minus bottom. I think I've got that correctly. No, I have it reversed, don't I? No, I think I got it. It's going to be in terms of y. Yeah, we'll go with that. Okay, so with all that said, we can plug in everything here. To calculate our radius, I don't know why I keep writing Tom, I just let it go. Let it go me. So to calculate this out, our radius is going to be dependent on the curve. So looking at our piece here, our radius is going to stretch from here up to here. If we do go top minus bottom, that's going to be y minus a -1. So there is our radius. And you can kind of tell that it's basically y units up, but then we have to add 1 back to get from the axis of revolution up to the x-axis. And then for our height, we will go right minus left. On the right, we had the x to the 5th, which will become x equals the 5th root of y. So we'll have the 5th root of y. And then on the left side, we're going to have what was radical. This will now be x equals y to the 4th. So we'll have that portion. As far as our volume then, we'll have our volume as 2 pi times the integral of, our radius will be y plus 1, and our height will be the 5th root of y minus y to the 4th, dy. As far as our limits of integration, they intersected at the points 0, 0, and 1, 1. So this will also run from 0 to 1, albeit in terms of y. So, ta-da. There's question D. That's going to next bring us to question 10, and I think it's sort of merciful that I get to do number 10 now. 10 is purely computational, so is 11. I'm really grateful for that. I'm just computing some integrals, so I'm going to move through quickly. I will note that question number 10 is focused exclusively around indefinite integrals, so we're just computing antiderivatives and remembering the constant of integration. It's question 11 that has the fundamental theorem of calculus in. So in here, we're going to do each term one at a time. I will start out, though, by rewriting the integrand, so that way it's in better position for us to antidifferentiate. I'll start with x squared. That one stays the same. Nobody cares. The next one is already written in sort of easy to antidifferentiate form. Thank you to whoever wrote that. That'd be me. I'm not sure why I did it, though. And then the last one I'll write is minus 5x to the 1/2, just so that we can see the powers. Now, given all that, we'll go one term at a time. The integral, or the antiderivative of x squared, is going to be 1/3 x cubed. The integral of the next one is going to come if we add 1 to the power. So that's going to be -5. So we're going to get minus 3 over 5 x to the -5. If you're having trouble seeing what happened there, that's because this is going to be 3 times 1 over -5, x to the -5, and then you can kind of follow everything else from there. And then last but not least, on this other one that we have over here, we have minus 5x to the 1/2. I'll put the minus 5 there as a scalar, but we're going to add 1 to 1/2, which will give us 3/2. We multiply by the reciprocal, which will be 2/3. So we are going to have, in fact, 2/3. Let me make sure I'm doing this correctly. Yeah, I'm doing it correctly. 5 times 2/3 x to the 3/2, because we add 1 to the power. And last but not least, we include that constant c, because we don't know if there was a constant there. So we're covering all bases. As far as our answer, that's actually acceptable, but I think we can clean it up just a tad. I'm going to write this as minus 3 over 5 x to the 5th, even though based on this, I probably should just leave it that other way. It's my fault for continuing to do it. I just don't value my time. This will be minus 10/3 x to the 3/2. And then finally, all of it is plus c. Voila. The next problem we're going to attack is going to be question 10b. 10b could be done using substitution. Like you could use substitution twice. I'm not going to demonstrate it using substitution twice. I'm going to do the first of these integrals using substitution, and then I'll do the second one without. So that way you get a flavor for each of those. So to kick things off, I'm going to just write out this integral with two colors. This is going to be the integral of two things dt. I'll do in pink 3 sine of 5t. And then on the other portion, I'm going to do this as plus, and you'll see why in a second, -5 cosine of 3t. So there they are. So the first integral I'm going to focus on, I'm using like the anti-sum and difference property here for a second. I'm going to focus on the integral of 3 sine of 5t dt for a second. In this case, if we choose to do that, the 5t on the inside is what sort of causes us problems. So just in case you're not comfortable executing this on your own, you can let u equal the inside. You can then term du to be the derivative of the inside. In a sense, you're basically lining up all the pieces for the chain rule to work out. Given this, we could also divide both sides by 5 and get that dt is equal to du over 5. So in here, that's going to, if we bring out the scalar of 3, we're going to get sine of u in the integrand, and dt will be replaced by du over 5. So of course, this is going to get us two things. It'll get us that scalar of 3/5. And then we ask ourselves, what function has derivative positive sign? And I'm hoping that you recognize that as negative cosine. So we'll get negative cosine of u as our thing, obviously plus c. But we need to replace u and get this back into our original form. So I'm going to do both, pull out that -1 scalar and make this -3/5 cosine. But then I'm also going to replace the argument with 5t. So the first integral, and again, including plus c, we probably shouldn't include that till the very end, but I'll mark it on there. There's the integral of the pink portion. So cool stuff. For the other one then, like how would we do the integral of -5 cosine of 3t? Well, I'm going to make one little move just to kind of make something clear. I'm going to pull out that 5, and I'll make this 5 times the integral of negative cosine of 3t dt. Now the reason I'm doing this is that I'm thinking to myself, what function has derivative negative cosine? And of course, the function that has derivative negative cosine is negative sine. So this will be negative 5 times the sine of something. But in particular, it's going to be negative 5 times the sine of 3t. Now, having said that, you can already tell if you differentiate this, you don't get the same thing. That's because we also need to account for u, and specifically du. So before dt ended up being equal to du over 5, this time it's going to be equal to du over 3. So I'm going to divide both sides by 3. And if you differentiate that, you'll see that this does indeed get us the expression we wanted. Now in this problem, they were asking us what is the antiderivative of that function. So I'm just going to point out here that the antiderivative they were looking for has two negative terms. It's sort of negative. That's life. We'll have negative 3/5 cosine of 5t. And then on the other side, we're going to have minus 5/3 sine of 3t. And then before you're like, cool, I'm done, let me move forward, don't forget plus c. There is our antiderivative. Now, if you don't trust this, you can always differentiate it and see if it works out nicely. In fact, I think that's still how I was kind of trained from high school, is just to kind of imagine differentiating at every juncture of one of these substitution problems, and eventually I'll get it. But there's a nice mechanical algorithm to get there if you're getting your feet wet again for the first time. For question C, this one's a more classic substitution problem. I'd love to just do this straight up. I think it's 5/6 x to the 3x squared plus 1. But just in case, I'll demonstrate u substitution more cleanly. I just really want this done, and I think this is appropriate here. So if we choose u to be the power of e, sort of the thought process being that the derivative of e, or the antiderivative of e to the x is e to the x plus c. We want to get this so it just says the integral of e to the u. So I'm going to let u equal that whole power, 3x squared plus 1. That means du is going to be 6x dx, which is the same thing as saying du over 6x is going to equal dx. Get our nice little conversion factor. Bringing this all in, our integral will become 5x e to the u times du over 6x. And notice that the x's are going to divide away. Wouldn't that be nice if in real life x is always just paired up? That'd be great. We'll have a scalar of 5/6 out in front, and then we'll have the integral of e to the u du. Now this just asks us what function has derivative e to the u, and that's e to the u. E to the u, better believe it. And of course plus c. But the problem here continues, it does remain. The problem is u. We started with x's. We need to have our final answer with x's as well. This will give us 5/6 e to the 3x squared plus 1, all plus c. So there's sort of a classic u substitution integral. It didn't have multiple pieces going on. So this would be on the easier end of the substitution type question I could ask. The last one we're going to look at isn't actually particularly difficult. It's just a test to make sure you know your reciprocal trig function derivatives and antiderivatives. So in this case, sort of what happens before you start, other than remembering plus c, in your brain you recall several of the trig derivatives to kind of prepare yourself. So hopefully what you'd think about here as you look at secant squared is you'd remember that tangent of theta's derivative is equal to secant squared of theta. And likewise, when you see negative cosecant theta cotangent theta, I'm hoping that you remember that this is the derivative exactly, by the way, of cosecant of theta. So both of these have the exact right sign to be the positive versions. In fact, this will be equal to tangent of theta and then plus cosecant of theta. And of course, yeah, don't forget plus c. So there is our antiderivative. So here there wasn't any sort of intensive use substitution. It was recognizing derivative rules and knowing what to do with them. Very important skill for sure. Okay, the last little section that I'm going to do here, I think I can make it through. I really want to do it. Am I even recording? Oh, thank goodness I'm recording. Is I'm going to do the fundamental theorem ones. I'll have to do the calculator ones another day. Maybe I can figure out a way to get my calculator back. So with that said, the fundamental theorem is basically the same as our previous problem with the indefinite integrals. We're going to anti-differentiate first. The difference is the fundamental theorem then has us evaluate that antiderivative at two different values, the upper and lower limits of integration respectively, and then simplify as much as we want to or feel comfortable doing. So to give you an idea, here's exactly how our process works for what's known as the FTC. It's going to almost always be the way that we evaluate these things. So first we compute the antiderivative. So our antiderivative here is going to be 6 times 1/3 x cubed plus 5 times 1/2 x squared. And if I simplify this a little bit, I'm going to get 2x cubed plus 5 halves x squared. And then I'm going to evaluate this from -1 to 2. So as a heads up, this is going to be a little bit crunchy. I think that was partly why I wrote this a couple days ago, was to be crunchy, just to remind you that you do have to be careful in here. So first, if I plug in 2, I'm going to get 2 times 8, which is 16, and then plus 5 over 2 times 4, which is 20 over 2, or 10. So that's pretty simple, worked out really nicely. On the next one, if we plug in -1, we're going to get 2 times -1, which is -2. The next one will be positive. It'll be 5 halves times 1, which is 5 halves. Now from here, just kind of cleaning things up, by the way, this is 26, and over here we have 2½ minus 2, which is going to leave us 1/2. We could have also done 5 halves minus 4 halves. We get just 26 minus 1/2. All of these are basically correct answers, by the way. We can stop at this point in the AP Calculus world at least. But if you do want to simplify this a little bit or further, you could call this 25.5. I think that's actually a clever way to avoid having to do some sort of fraction work thing. Or if you preferred, you could call this 51 over 2. Both of those are perfectly correct, of course. So again, our key step here was instead of just stopping at our antiderivative, we then evaluated it at the two limits of integration and subtracted to find the difference. That difference represents the value of this definite integral. The next one we're going to look at is our first substitution one, and there are two different ways to do this, but I'm going to do it the fastest way out of all the methods, so just as a heads up, that's my goal. So in doing this with the faster of the methods, what I'm going to do first is I'm going to formally state that u is going to be the name of my variable I used to replace this, and then du is going to be 2x. Now I dove into that really fast. If your question is how did I recognize to choose to let u equal x squared plus 9, it is somewhat an experience-based factor. It takes a little bit of getting used to, and it helps that I've seen thousands of integrals, whereas you've probably maybe seen hundreds. I've probably seen tens of thousands of integrals. I'd guess that I have. But for you, that's not quite there. But what I notice here is I've got x squared plus 9, whose derivative would be 2x, and then there's a 2x up here. So I'm thinking this is set up for u substitution, so that's the route I'm going to go. The only thing I'm going to do, though, in addition to that, is I'm going to take this information and convert my two limits of integration. Right now, those limits of integration are x values, and I don't want them to be x values. I want u values, so I can do a complete swap around. So in this case, if x is equal to 0, then u is going to be 0 squared plus 9, also known as 9. And on the flip side, if x is equal to root 7, then u is going to be, it looks like 7 plus 9, which is 16. Now what I've just done is I've converted all the limits of integration and the integral itself, so I'm going to go ahead and start swapping things in. So effectively what we're going to have is that the integral from 0 to root 7 of 2x over the square root of x squared plus 9 dx, that is going to be equal to an alternate version of the integral. It's going to be equal to the integral from, it looks like, 9 to 16 of what is 2x over the square root of u. And then specifically here, it looks like du is 2x dx. So that means dx is going to be du over 2x. As mentioned earlier, the 2x's divide away. We end up with the integral 9 to 16 of 1 over the square root of u du. And as a heads up, that's equal to 2 square root of u. Should draw an imply sign. We'll evaluate that from 9 to 16. That's going to give me 2 times 4 minus 2 times 3, which I think is just equal to 2, right? 8 times 6, yeah. So the answer is 2. After all of that work and time and energy, the answer is 2. Question C in question number 11. I'm hoping this will be our last one. This is another substitution problem, but I think it's specifically related to a different type of function. So in this case, trying to decide what technique to go with, like what made me think of u substitution already. The derivative of the denominator is 2t minus 4, or a multiple of t minus 2, and I see a multiple of t minus 2 up here. And by the way, if you're wondering, like, oh, you only saw it that fast because you wrote the problem. I mean, yeah, I guess that helps, but I wrote it several days ago, and I'm so exhausted and tired and frustrated right now that I'm not thinking back to my thoughts on Monday morning as I was writing this thing. I'm just looking at structures, and I'm really comfortable looking at structures here because I've seen so many integrals. You know, score one for practicing a little bit, you know. So in this case, that's going to be my goal. I'm going to hopefully see this work. I mean, it's always possible that this won't work and I'll have made a mistake. But I'm going to let u equal t squared minus 4t plus 5. And then du is going to be 2t minus 4 dt. And now when I go to solve for dt, I'll get du over 2t minus 4 equals dt. But I'm going to go ahead and factor out that GCF of 2 to leave me a t minus 2. Like I did last time, I'm going to go ahead and convert the limits of integration as well. I'm big fans of that. If x is 0, u is going to be equal to 0 squared minus 4 times 0 plus 5, which is 5. And if x is equal to 3, then u is going to be equal to 9 minus 12 plus 5, which is equal to 2. So based on all of this stuff, we got some swapping to do. Our integral is going to transform into the integral from 5 to 2. It's going to be of what is 3 times t minus 2 all over u times our dt, which is right here. dt becomes du over 2 times t minus 2. And now you too can see what I was going for. The t minus 2's divide out, and we have a scalar of 3 halves to bring out in front. This will be 3 halves times the integral from 5 to 2 of what looks like 1 over u du. And of course, once we're here, we can see this really fast. This is 3 halves times the natural log of the absolute value of u. We're going to evaluate that from 5 to 2. If I clean this up a little bit, I will have 3 halves. It'll be 3 halves times the natural log of 2 minus the natural log of 5. And from here, that's a perfectly good answer. That works out great, but I could clean this up a little bit. I could write this as 3 halves times the natural log of 2/5. Or if I wanted to write this in sort of a different looking version, we could have negative 3 halves times the ln of 5 over 2. Both of those are correct. I would suspect this would be the answer choice you'd be given, maybe even this one, but I think the boxed one would be the correctest one. So tough problem at least when you first start, but I think seeing that denominator with those 3 terms and the derivative with 2 terms, I think a good strategy for right now where we're at. Eventually we'll learn partial fractions. But for now, a good strategy is to aim for substitution. That's really the fanciest, most sophisticated technique we've got. So why not? Oh, and there's one more here. Let's finish this up. I think this is a pretty clean one. Just to get some trig ratios in there. I think that was why I tacked this one on at the end. We want the definite integral from pi over 6 to pi over 3 of 4 cosine of x. As a heads up, if you wanted to picture this function, you would be able to. Cosine looks like this. And in particular, pi over 6 is here, and pi over 3 is here. So we're effectively asking, what is the numeric area in this region? And although it might seem sort of daunting, considering the fact that this isn't like a familiar geometric shape, super easy. We know the fundamental theorem. So 4 cosine of x is the derivative of 4 sine of x. So that makes 4 sine of x its antiderivative. We're going to evaluate this from pi over 6 to pi over 3. That's what I was going to say, it was 3. This will be 4 sine of pi over 3 minus 4 sine of pi over 6. Now I know trig isn't every person's favorite thing. That's too bad. Trig is kind of cool actually if you look at it pretty closely. But if you don't remember your trig, that's actually going to hurt you in this case. You do have to evaluate any functions. I expect you to get the value of sine of pi over 3. But for the moment, I'll do it for you. Sine of pi over 3 is root 3 over 2. And the sine of pi over 6 is 1/2. Like I would love to see that just as stopped right there. This does simplify to 2 root 3 minus 2. There are, of course, other ways that you could clean this up. We'll go with this one. And with that said, I think that's going to end what I can do tonight. Yeah, that brings us to 12. Could I do 12? I could probably do 12, but I don't have a calculator handy, so I'm going to stop right now. That's going to conclude the third part of this video. I'm just doing every little bit that I can. Yeah, thanks for watching. Bye.